So we're going to add in the work if there's an external force like friction. So the kinetic at A plus the potential at A equals the kinetic at B plus the potential at B plus work. That's it. You just add the work to the equation. And you'll notice that I did include that in the equation up here. Now, the reason it's in parentheses, as I mentioned, is because it's not in every problem. It's in many of them, but not every one. So don't assume there's work. And if it doesn't say work, it's not in it. If it doesn't say what's the work done, or it doesn't say the work is this, then there isn't any. Okay? Now, there's a reason why it's plus instead of minus. You might be saying, hey, friction does negative work. It slows things down. The reason why it's plus and not minus is because I made this the quote-unquote missing energy. So let's say I set up a problem and I got, I don't know, like 30 equals 27. Well, obviously 30 does not equal 27. So where's the extra 3? The extra 3 is the plus work. And that would be equal to 3 for this problem, because it's the quote-unquote missing energy. Okay, so let's do example B. Let's set this one up. Let me show you what happens for a problem like this. So the exact same problem we had before. So I'm going to save us some time a little bit because it's the exact same problem that we had. So a roller coaster, mass is 0.5 at the top of the hill, 4 meters. Okay, 4 meters above the ground. Okay, travels down through a valley and travels back up to a second hill that's 3.5 meters tall. However, because of friction, the roller coaster stops when it's at a height of 3 meters. How much work was done by friction for this to be a case? So we can assume it started at rest again. And it's also going to end at rest because it says it stops. Okay? So once we've drawn and labeled our stuff, and here's the mass still 0.5. Okay, here's A, same as before. Here's B, same as before. Most of you I saw picked the ground to be 0, so I'm going to do that. You can certainly do the same thing you did before, though, so if you made B 0, you can do that again. But do notice that B is not at 3.5 now. B is at 3. So, next step. Find potential and kinetic energy at A and B, just like before. So the kinetic at A, 1/2 mv squared. 1/2 times 0.5 times the velocity at that point, which is 0 squared. Kinetic A is 0. Potential at A, mgh. So 0.5 times 9.8 times 4. And it's the exact same number we had before because it's the same, exact same everything. So that number was 19.6. Okay, now we're going to do B. So B is 1/2 mv squared, which this time is 0. It's not an unknown. It's 0 this time because it says that it stops. So that's 0. Potential energy at B, mgh, but this time the height is the height is 3. $14.7. So if I set up the equation I did originally, I'm going to leave off work just for a second. if I set up the equation I did originally, it's going to look like this. 0 plus, so kinetic at A plus potential at A, 0 plus 19.6, equals kinetic at B plus potential at B, 0 plus 14.7. You'll notice that 19.6 does not actually equal 14.7, believe it or not. So what's missing? Work. Subtract 14.7 over. Work is 4.9 joules. There you go. So again, even though friction does negative work, and we know it does negative work, the reason I did not plug in a negative number and the reason why I did not get a negative answer is because I'm treating this as the lost energy. Okay? I'm looking for what do I need to add to 14.7 to get 19.6? Again, energy cannot change. The total energy before has to equal the total energy after. 19.6 can't equal 14.7. So where's the extra energy? It's work. So I add it in, and you get those two things to get this. Again, as I kind of mentioned before, it's actually more correct to say plus W at the beginning. But most people forget that work needs to be negative in those circumstances, and so I find treating it as the missing energy is a little simpler. So, turn to the back page. Okay, you got two problems on the back, just like on the practice A. So, a 900 kilogram stunt driver is driven off the top of a 50-meter cliff with a velocity of 25 meters per second. If the wind resistance against the car does 50,000 joules of work, find the car's velocity when it's 25 meters above the ground. So you're going to set this up and solve it similar to what we've talked about for those values, but make sure you include the work done by air resistance. And then you have 2, which is BMX biker reaches the bottom of a 10-meter ramp going 14 meters per second. To the disappointment of all, he only makes it 7 meters up the ramp. How much work did friction do on him? And it's the same kind of idea. In this case, though, you're trying to solve for the work instead of being given the work. Just depends on what the problem is. Any questions for me?